Okay, so now we have Fredrik Malmberg from KTH, and he'll be presenting temporal denoising of 3D reconstructed hand pose sequences. So let's welcome Fredrik.
All right. Hi, everyone. So this title is quite a handful. I'm going to try to keep it high level. When I saw that I was the last one presenting before the coffee break, I was a bit disappointed. But the good thing is that I think you've all gotten a pretty good primer, so it will be much easier to understand what I'm talking about here. So this is about temporal denoising, and we've heard about different sorts of data, 2D data, 3D data, and the problem with data, that we don't have enough data, that the data is bad, and so forth. So the idea here, this is a work in progress. So we have worked on a temporal denoising method that converts noisy 3D hand pose sequences reconstructed from 2D sign language videos. And the idea is to create smoother sequences that we can use for generative sign language models. And I don't know if you remember, you saw these simple X models, typically gray or bluish, and the hand models, the Mano model. You also saw some of the videos of the reconstructions where you could see some jittering and some unstable sequences. So that's what we're trying to solve here. And why do we need this? Well, in our lab, we work a lot with mocap. We work with 3D and avatars. And the reason we think that's interesting is because it's good for driving avatars. We can use it in VR and AR and robotic applications as well. But when we train generative models, if we have unstable sequences with a lot of flickering and things like that, it tends to get very confusing for the models, and it's hard to learn. But this 3D motion data is very rare. I mean, most of the data sets you've seen today is 2D. So what do we do about this? Well, the most common approach, and the approach we've seen in some of the presentations today, is to use something like Hamer or Weiler to do a 3D reconstruction. And those typically operate per frame, which means that you do get jitter, you miss articulations, and you get unstable motions. And this image here is an example of that. That's the letter I in Swedish sign language. Yep. So the letter I. And in a typical video sequence, this does get reconstructed properly sometimes, but sometimes it fails, which means you get a pinky moving up and down like this, which we don't want. And just I'm guessing here, but it's most likely because this woman has long hair, which confuses the model, because sometimes it thinks it's a finger, and sometimes it probably thinks it's just a hair falling down. But we as humans, we know that it's a finger if we watch the sequence. It's not a problem for us. So the proposed approach to kind of fix this problem is to use these existing single-frame 3D reconstruction frameworks, like Hamer or Weiler that we talked about earlier here, but then apply a temporal denoiser to fix this. And the temporal denoiser's task is to better understand the human motion, to understand that the pinky cannot move up and down infinitely fast between frames. And the idea is that we get out temporally stable 3D hand pose sequences. Right, so how do we train this temporal denoiser? Well, in our lab, we do a lot of mocap capture. What you typically have is a person dressed in black. We use gloves to capture the hands, and we get out a 3D representation as a stick figure. We take that representation, we retarget it to the simple X model, and then we render out videos of that sequence. In this case, we used Blender for that. And the good thing is that these sequences, they don't have to be photorealistic. They just have to be good enough so we can run the reconstruction framework on them. Because when we run Hamer, in this case, we get noisy samples. So what we render here is something that's not really photorealistic video, but something that tries to capture or tries to kind of find the same failures as Hamer typically suffers from in regular video. Right. And the model we use for this is residual UNet, and this is quite a technical slide. I think I have a poster spot, so feel free to come up and talk to me about this. But in short terms, we're using this to kind of denoise the entire sequences. So it takes in the noisy sequence and it tries to predict the residual, i.e. what's needed to kind of correct the sequence to become a clean post sequence. What we also do that's specific to this is that we condition it on the wrist positions. And the reason we include the wrist positions is because we want to inform the model of two things. One is that fast wrist movement is typically indicative of motion blur, which is one reason that Hamer fails. And the other is that you get self-occlusion. If one wrist is in front of the other, you're typically occluding one of the hands. And we also do some things around the loss, more than just trying to reconstruct the clean sequences. So we try to enforce that the model is not correcting everything. So we use residual regularization on the sequence, and we also try to enforce velocity and acceleration consistency, because what we really want to capture here is the motion dynamics of the original mocap sequence and not the absolute hand pose for each single frame. And we tested this on the Signify data sets, and even though we used Swedish sign language for the mocap data capture, and Signify is German sign language, we were able to improve the results that Hamer got standalone on the single frame reconstruction. And these numbers are maybe underwhelming in a sense, but if we look at the graphs, we can see that in cases where we have higher wrist velocity, we're improving more on the single frame reconstruction, which is the idea behind this, that high motion blur can be fixed or at least improved on with this type of model. So in conclusion, this work, and hopefully we can improve it even further, could potentially enable large-scale and more temporally stable 3D sign language data from 2D video. And this is important. For us, it's important because we train generative models. Hopefully other people find good 3D data important. And it could also be used for other post-reconstruction tasks. But as I said, there is still room for improvement. I think we can do a lot on the optimization, the model architecture, the amount of data we have. So there is a lot of work to be done. And more specifically, I think what we really need to do as a next step is to do human evaluation to see whether we're actually improving these sequences. So now we just did quantitative because it was faster, but we want to make sure that we're not destroying the expressiveness of these sequences. So that's all from me. If you have any questions, feel free to come to the poster or ask me now.
Fantastic, thank you.
Thank you.
It was a great presentation. Thanks very much. It's very relevant to some of the stuff that we're working on. Does anybody have any questions? Oscar first.
Yeah. Thank you. Yeah, I agree. Very relevant work. I was wondering, you said that you just did machine evaluations, but did you notice any cases through that evaluation where your model actually deteriorates the original inputs? Like, is there any kind of failure cases that are actually introduced by this model?
Yes. The problem with these things is that you typically get some over-smoothing. So, for instance, with the pinky, I can show you a video later. I just need to find it. There is the case where the finger is not moving up and down, but it's not straight either. So you kind of get this like crooked pinky, which is better in some ways for the generative models because you're not introducing these fast fake movements, but you're also losing expressiveness. So there's definitely something there. And potentially now we trained it with only 4 or a bit more than 4 hours of mocap data. So with more data, it could be improved on potentially. So there's a lot of work to be done, but there is still some. It is more temporally smooth. Yes.
Thank you.
Leo, do you have a question?
So one thing I noticed with Hammer, one flow, except for the handshake and precision, is that often since it's done like hand by hand, it crosses around a hand. When you try to combine both hands together, the depth is a bit off, like it can be non-consistent between two hands. Did you notice that your model, by refining both hands at the same time with the wrist position, allows to sort of fix this kind of depth and consistency?
Yes. So the question was that since Hamer is doing frame by frame, you're getting different camera poses and you're also getting different absolute positions of the wrists, which is challenging. Was that kind of what you asked? Yeah. And we didn't start looking at that. At this point, we're only dealing with the hand joint rotations. So we're just taking the global position of the wrist from Hamer, and we say that's fine. So I think a natural next step is also to include the rest of the body in this temporal denoising. But we started with the hands. So we don't fix that. I'm sorry.
We have time for one more question. Okay. Yep, I'll speak again.
Yeah, I was wondering, like your method relies on the fact that like your input capture with your glove is kind of error free, right? Is that actually the case?
No, of course not. No. We can. Yeah. Okay. So the question was that the data that we capture in the mocap lab with the gloves is free of errors, and that's definitely not the case. I would say it's the motion is good, but the absolute joint rotations is not perfect. But since we're using this combined loss where we focus a lot on the velocity and acceleration consistency, I think we solve a little bit of that. Ideally, we would have perfect data, but no. We're working on that in parallel. Actually, my colleague Anya, who's here, she has a poster where she can tell you everything about how our mocap setup works. So.
Thanks.
Okay, let's thank Fredrik, and you have a poster, so
Yeah.
you can ask more questions. Okay, so now we'll have a break until I think it's 11:30. This break will also be the poster session.